pressure altitude. So this is your airport, okay, and the elevation of this airport is 4,000 feet. The elevation is always measured from QNH, that is mean sea level. So let's draw this mean sea level, where the QNH is equal to 900 millibars, okay, and elevation here is equal to 4,000 feet. QNH 900 millibar. What is the pressure altitude? Now pressure altitude is always measured from standard pressure setting pressure level 1013. So let's draw that. This is your standard pressure setting 1013. So pressure altitude will be equal to elevation, this much elevation, plus extra this. Now this extra value is nothing but the height difference between these two pressure levels, QNH and standard pressure setting. Okay, so I'm going to write it here. Pressure altitude equals to elevation plus the height difference between two pressure levels. So what is the pressure difference between them? 1013 minus 900. 1013 minus 900, that is equal to 113. So that is the pressure difference between them. This pressure difference will be equal to a height difference of 113 into 27, that is 3051, or approximately 3050 feet. So your pressure altitude is gonna be elevation 4000 plus a height difference of 3050. So that gives you a value of 7050 feet. So pressure altitude equals to 7050. Next, question 12. Field elevation is 3500. QFE is 1020. What is the pressure altitude? So let's draw this diagram. This is your airport. QFE here is equal to 1020. Okay, elevation is always measured from mean sea level, QNH. So let's say QNH is this. Elevation is equal to 3500. Okay, 3500, and we are told to find out pressure altitude. Now pressure altitude is always measured from standard pressure setting 1013. Now you can see here QFE is 1020. Standard pressure setting value 1013 is going to be located above QFE 1020, because as you go to higher altitudes, atmospheric pressure decreases. So 1013, which is less than 1020, will be found above 1020 pressure level. So I'm going to draw standard pressure setting value 1013 above the airport. Above the airport. Okay. So what is going to be the pressure altitude? So pressure altitude is measured from standard pressure setting 1013, from there to this airport. Now, so this height difference between these two pressure levels 1013 and 1020 is equal to how much? So this height difference is nothing but equal to the pressure difference. Pressure difference here is 1020 minus 1013 is equal to 7 millibar. Now 7 millibar is equal to approximately 210 feet. 7 into 30, 210 feet. But you are going to add a minus sign here. This minus sign denotes that the airport is below this pressure level, 1013 pressure level. Okay. So answer is minus 210. So let's check it again. Field elevation 3500 and QFE 1020. Fine. So what is QNH? Let's find QNH also. So here the height difference between two pressure levels is 3500. right? So 3500 is equal to a pressure difference of 3500 divided by 30, which is 116.6, or 3500 divided by 27, that is 129.6, or approximately 130 millibar. So QNH will be equal to QFE 1020 plus this pressure difference of 130. 1020 plus 130, that is equal to 1150 millibar. Why have you added this? Because as you go to lower altitudes or lower levels, okay, the pressure, atmospheric pressure goes on increasing. So therefore 1020 plus this pressure difference of 130 gives us a QNH of 1150. Question number 13. Pressure altitude is 3700 and QNH is 1000. What is field elevation? So let's consider this is your airport. Now QNH, pressure altitude is 3700. So this is your mean sea level, let's say, where there is QNH. This is your standard pressure setting 1013. Pressure altitude of this airport is 3700. Pressure altitude is measured from airport with standard pressure setting value, that is equal to 3700. Field elevation QNH is 1000. Now field elevation, what is field elevation? Field elevation is nothing but this, this value or this height. Now this height is equal to this big height minus this small, correct? So that small value is nothing but the height difference between these two pressure levels. The height difference between these two pressure levels, 1000 and 1013. So what is that equal to? So this height difference is equal to how much? So what is the pressure difference? 1013 minus 1000, that is equal to 13 millibar, right? So 13 millibar is equal to 13 into 27, 351 or 350 feet. So this height difference is equal to 350 feet. Now the elevation is equal to pressure altitude minus height difference. Pressure altitude 3700, a height difference of 350. So elevation will be equal to 3700 minus 350, that is 3350. 3350 feet. Okay, so this is the field elevation which is measured from QNH. Takeoff and landing performances must be calculated based on dash and dash respectively. So always remember, takeoff performance calculations are done on the basis of or with the help of ambient conditions. That means the conditions that are currently existing at the airport. Because you're going to take off after some time, after a few minutes or after half an hour and so. So you're going to have the latest reports, latest temperature conditions, atmospheric conditions, etc. But landing performances will be calculated based on forecast temperatures, forecast conditions. Now you're going to land at your destination after some time, after 1 hour, 2 hours, whatever. So the record, the numbers or the records that you're going to have will be the forecast numbers, forecasted temperature, forecasted pressure, forecasted this, that, etc. Right? So takeoff calculations or takeoff performance calculations are based on current conditions, real-time conditions, and landing performances calculations are based on forecasted information, forecasted data. Okay, so remember this. Next, if the outside temperature at a pressure altitude of 5000 feet is 10 degrees Celsius, what is the temperature deviation? Simple question. So temperature deviation is equal to outside air temperature or ambient temperature minus ISA temperature. So outside air temperature is 10 degrees Celsius. ISA temperature at 5000 feet. So ISA temperature at 5000 feet equals to 15 degrees Celsius minus 2 into 5. So 15 degrees Celsius minus 10 degrees Celsius, that is equal to 15 minus 10, 5 degrees Celsius. That means the ISA conditions state that at 5000 feet you must have 5 degrees Celsius temperature. But what you actually have is 10 degrees Celsius. So 10 minus 5 is 5 degrees Celsius. That means temperature deviation is equal to 5 degrees Celsius, which means outside air temperature is 5 degrees Celsius warmer than ISA temperature. 5 degrees Celsius warmer than ISA temperature. Density altitude is the altitude at which existing density would occur in ISA, the density at which existing temperature would occur in ISA, the elevation at which existing density would occur in ISA, the pressure altitude corrected for density deviation. So density altitude is nothing but pressure altitude corrected for non-standard temperature. So pressure altitude plus 120 into ISA deviation. I have made detailed lectures on density altitude, and you can find those two video lectures in one of the playlists, maybe RK Bali GenNav playlist or Oxford GenNav playlist. So in that two videos, I have explained the concept of density altitude, its applications thoroughly. So do watch those two lectures. In short, if I have to explain this again, density altitude is nothing but the altitude which your aircraft engine thinks it is located at. So your aircraft may be located at mean sea level airport, okay, mean sea level. But if the temperature at that airport is warmer than ISA temperature, now ISA conditions state that at mean sea level the temperature must be 15 degrees Celsius, 1 5. But if the actual temperature or ambient temperature is warmer than that, meaning 30 degrees Celsius, 25 degrees Celsius, if it's warmer than that, so the airplane will perform or behave according to that temperature. So now let's say you are at pressure altitude, mean sea level, and the temperature over there is equal to 5 degrees Celsius, or let's say it's warmer than that, so 15. So let's say it's 20 degrees Celsius or something like that. Okay, it's warmer than 15 degrees Celsius. So 20 degrees Celsius, 30 degrees Celsius, whatever. So if it's warmer than actual temperature, warmer than ISA temperature, so what will happen? The warmer temperatures means less density, right? Warm temperatures or hot temperatures decrease the density of air. If air density decreases, what happens? Aircraft performance will get affected. Your aircraft engine power, thrust, rate of climb, everything will get affected. You will require longer takeoff distances, longer landing distances. So this decrease in density will affect your aircraft performance. So although your aircraft is at mean sea level, but the performance that it generates will be according to it will be according to an altitude where you're going to find this density. So the density at mean sea level is, let's say, equal to density which is normally found at 10,000 feet. So that means the aircraft will behave according to the 10,000 feet altitude. It will start showing behavior, or it will start performing in a way that this aircraft behaves when it is at 10,000 feet. So notwithstanding the fact that your aircraft is at mean sea level, it will show performance numbers which are likely to be found at 10,000 feet. So that is a very big disadvantage, because when you go to higher altitudes, air density decreases. Okay, and to enable your aircraft to fly at those high altitudes where density is very less, we have jet engines, we have pressurization system. But at mean sea level, if you're flying a general aviation aircraft, you don't have those equipments or that technology. So the performance given by your aircraft will get severely affected if density altitude at your airport is much more than pressure altitude. So that is nothing but density altitude corrected for ISA deviation. ISA deviation is nothing but the temperature difference between ISA temperature, what ISA says, and the temperature that is currently outside. Now, if outside temperature is colder than ISA temperature, so it's very good. It's good news. So the density altitude in this case will be less than pressure altitude. Okay, so it's less than pressure altitude. So that means the density of air is much more than what ISA conditions ask or demand. So more density means better aircraft performance, better performance calculations, short takeoff distances, shorter landing distances, like that. Okay. So the correct answer is the density at which the existing temperature would occur in the ISA and the elevation at which uh, altitude at which existing temperature, yeah. So, so the elevation at which existing density would occur in the ISA. Next. The pressure altitude of the field can be found by setting QNH on the altimeter, setting QFE on the altimeter, setting 1013 on the altimeter from air data computer. So pressure altitude is obtained. So we have solved so many questions by setting 1013 in your altimeter setting window. When you set QNH, you get altitude information or elevation of the airport information. Upon setting QFE, you will get your height information with respect to the ground below you or from the airport. Okay. If field pressure altitude is 5,000 feet and outside air temperature is 25, what is the density altitude? So density altitude is nothing but pressure altitude plus 120 into ISA deviation. Okay. So pressure altitude is 5,000, ISA deviation. ISA deviation is nothing but outside air temperature minus ISA temperature. Outside air temperature is 25. ISA temperature at 5,000 feet is 5 degrees Celsius. So 25 minus 5 is 20. So 120 into 20 is equal to 7,400 feet. So although you are at pressure altitude of 5,000 feet, aircraft thinks it is at 7,400 feet. So the performance generated by it or shown by it will be equal to performance that it is expected to show at 7,400 feet. So that is a disadvantage. Next, QFE 1022. What is pressure altitude of the field? So QFE is nothing but aerodrome level pressure, right? So QFE is 1022. Standard pressure setting 1013, which is less than 1022, will be found above that pressure level because when you go to higher altitudes, pressure decrease. Okay, pressure decreases. So pressure altitude will be equal to how much? Now the height difference between these two pressure levels is nothing but equal. It depends or it's directly proportional to the pressure difference. So pressure difference is 1013 minus 1022. So that is equal to 9 millibars. 9 millibar will be equal to 9 into 27, which is equal to 243 feet or approximately 240 feet. That means the pressure altitude of this airport is minus 240 feet. Why minus? Because this airport is below the standard pressure setting level. So minus 240 feet. If QNH is 1000, elevation is 4500, what is QFE? So let's draw this diagram. Airport, mean sea level, QNH, 1000, elevation 4500. Now QFE is nothing but aerodrome level pressure. So how can we find that out? We can find that out by converting this height difference between the two pressure levels into a pressure difference. So the height difference here is 4500 feet. That is equal to a pressure difference of 4500 divided by 30, approximately 30, that is equal to 150 millibars. So 150 millibars, that means QFE will be the pressure, QFE pressure will be equal to QNH minus pressure difference. So 1000 minus 950. So 1000 minus 150, correction, is equal to 850 millibar. Okay, so the pressure at airport or QFE will be equal to 850 millibar. That's it. So this concludes the lecture. I hope you have understood all the 10 questions, the answers, how to answer them, the formula that I use, the concept, the explanation. If you still have any doubts or questions, let me know in the comment box. Thank you for your time. Best of luck. In my next video lecture, I will solve the next 10 questions. So do watch that video lecture.